Hello everyone, I am Ravi Pratap Singh, Assistant Professor at Department of Mechanical Engineering, ABES in Ghaziabad. Today I am going to explain the basic procedure for solving numerical problem using finite element method. This is part 1 of 4-part lecture series. In part 1 I am going to explain the basic steps for performing the finite element analysis. In part 2 I will be covering the numerical problem related to structure in 1 dimension. In part 3 I will be covering the structure problem in 2 dimension, and then in part 4 I will be covering the heat transfer problem. Okay, coming back to part 1, the finite element method is used to solve various engineering problem, maybe in the field of structure, maybe in the field of heat transfer, or maybe in the field of fluid flow. The basic steps for solving any class of problem which I am mentioning, they require these 9 steps. The basic difference between different process parameter may be somewhat different, like especially the application of boundary condition and the computation of elemental stress strain or parameter which are required. For any finite element problem, the following information the candidate would be having before solving the problem. These information consist material data or material properties, geometrical data, then external force information, then external boundary conditions information. These are the input parameter which you need to supply or use in the solving the numerical problem. Based on these data, using finite element steps, we need to find stress, strain and reaction force on the each element or each node at particular problem. These given data or information which need to be we are going to supply, these are also used while solving the finite element problem using any commercial software like ABES or NISA or ANSYS. So these steps consist starting from step 1 to step 9. Suppose we are having a 1-dimensional bar element. The material data we are having, let's suppose E is given 30 GPa. Geometric information or geometric data, here the length of total element is 3 meter. External force information, at the end, at free end of this element we have 20 Newton force. And the boundary condition, at the left face the bar is fixed. Okay, how we start solving this problem? Firstly, we need to go to step number 1. Step number 1 says we need to discretize the whole element into small sub element. As the student who have taken the course on FEA, they know that in finite element method the basic challenge is to discretize the whole problem into small element, because we are going to solve each and individual small element. Those information which we obtain from those small element, we are going to integrate in mathematical sense, but here we are not going to deal with mathematical sense, only in abstract sense solving the numerical problems. In first step, discretize the problem. Discretize means, suppose we are having a force at this location. The distance from free end is about 1.5 meter. The basic idea of discretization is to include all forces, include all external forces, include all boundary condition. In finite element, each and every problem we solve, we need to figure it out that these two information, external boundary condition and external force, must coincide with a particular node. To get a particular node at that point of application site, we need to discretize into small element. In this case, we have discretized this problem into 3 small elements. Element 1, 2, 3. The basic difference between, there are 2 kinds of numbering. 1, 2, 3 without circle and 1, 2, 3 with circle. The information which portray with circle, they depict or they says the numbering of element. Like the whole length is 3 meter, we have divided into 3 small elements. Every small element has 1 meter length, 1 meter L1, 1 meter L2, 1 meter L3. And once we have given the element numbering, then we need to define the nodes. For example, node number, element number 1 is here. For element number 1, we need to number from left to right. Here numbering start from 6th edge, node number 1, then it would be second, For second element, it will start from second, so second and third. For third element, start from third, so third and fourth. Why these numbering are very consecutive? Because we have divided this whole element into a small part. So it's in global sense, numbering would be 1, 2, 3 and 4. Then once we have a small element, then we need to find out the basic element information like stiffness matrix for local element 1, then force vector, local force vector for element 1, then nodal displacement vector for element number 1. And in that sense, element number 2, element number 3, then we need to find the global format. Then step number 2, once we have discretized the problem into small element, then we are going to find out the elemental stiffness matrix. The elemental stiffness matrix, it solely depends on the type of formulation which you have used. Here we are solving the one-dimensional problem. So the basic formula for one-dimensional problem would be K is equal to EA by L 1 1 minus 1 minus 1. This formula is derived using various methods which are included in finite element analysis. Element number 1, we need to derive K1, element number 2, K2, K3. Once here I am saying K1, K2, K3 because element number 1, it's this K1 is giving information about this local element, K2 is giving information about this element, K3 is about this element. Once we have found out the local contribution of their element stiffness, then we need to find out their global sense because these elements are solely connected, but here we are figuring it out only locally. We have separated element 2 from element 3 or element 1 from 2 and 3. So once we have discretized it, then find out the local stiffness matrix, we need to assemble them. Assembly does not mean that you need to only add the matrix because here the matrix size would be around 4 cross 4. You need not to assemble those matrix or add simultaneously. You need to assemble. Assemble means you need to, there may be possibility sometimes you need to add two information or nodal information, or sometimes you need to subtract those nodal information. How to assemble, I will cover in the part number 2. Once we have discretized it, then formulated the stiffness, local stiffness matrix, assemble them. Then second information we need is information about force vector. Here I have said that we have divided our original problem into 3 parts, 1, 2, 3. We have find out the K1, K2, K3 for individual element, then assemble the local into global sense. In similar way, we are going to find out the stiffness, the force vector for element 1, force vector for element 2 and force vector for element 3. So here we have find out the F1, F2, F3 for individual element. In again like global stiffness matrix, here we need to assemble the local force vector into global sense. So it's Fg. Once we have figured out K and F, then we need to find out the displacement, nodal displacement. As these problems are used to find out the deformation at any point of time. Let's for example this pen. Here I am applying X amount of force. I want to figure out that at this point of time, at this point, how much deformation is happening inside this element. To find out those deformation, I need to figure it out. This local nodal displacement vector for element 1, element 2 and element 3, like F1, F2, F3. Here we need to find out U1, U2, U3. Once we have find out U1, U2, U3, then again we need to assemble just like K, just like F, this U. Once we have figured out K means stiffness matrix, then force vector, then nodal displacement vector, we need to formulate assemble into the global nodal displacement load equation. This equation consists K, F and U. Ku is equal to F. In right hand side, you would be having the external forces which we are going to apply as stated in the problem, that force of 20 Newton. In the left side, you would be having stiffness matrix and the nodal displacement vector. Nodal displacement vector will give information about deformation and K will be giving information about material property and geometrical parameters. Once we have figured out the global nodal displacement vector, this is the initial formulation. Now we need to apply the last boundary condition. Boundary condition means in this problem the bar is fixed at left end. It means if we have parted this problem into 4 parts, 1, 2, 3, node 1, node 2, node 3 and node 4. I need to figure out deformation or U as node 1, U as node 2, node 3 and node 4. Here problem already stated that node 1 the bar is fixed. It means there would be no deformation. It means U1 is equal to 0. So in this problem, because this is a square matrix, U is a column vector and F is also a column vector. Okay, then in this column vector, in place of U1 we are going to write 0 because U1 is already known. U1 is equal to 0. Once we have figured out U1, then we need to cross that row and column. So why we are going to cross it? Because the unknown parameter of U1 is known at that point of time. It means given boundary condition help us to reduce the broad problem into small problem. Once we have reduced that problem, it means that problem is in the form of Ax is equal to B. A means that stiffness parameter, X means the various unknown field U1, U2, U3, U4 where you have already find out U, and B means the coefficient or force vectors. In step number 8, students are supposed to use different technique, like they can use either the Gauss elimination method, Gauss Jordan method, Cramer's rules, or any say method which they have already used in their mathematics course for solving the 3 equation 3 unknown, 4 equation 4 unknown, or 5 equation 5 unknown. In this FEA course, which is for UG classes, maximum this equation may be 5 cross 5 means 5 equation 5 unknown. Once you have find out the x means here the k is already given, everything, b is already given because they are the simple parameters in matrix sense. This x, you have figured out the x value of x in terms of u1, u2, u3. Then once you have find out the deformation at each node, node 1, node 2, node 3 and node 4, based on that information you can calculate using given formula for elemental stresses, elemental strain and reaction force at the support end, because reaction will happen only where we have provided the support. At the end, in summary, in finite element problem, the given parameter would be material, geometry, force condition, boundary condition. You need to figure it out, the stress strain reactions. Any cross-solve problem can be solved using these basic 9 steps. Steps consist from discretization, formulation of stiffness matrix, then global stiffness matrix, formulation of global load vector, then global nodal displacement vector, then using those K, F, U, formulation of global nodal displacement load equation, then incorporating the boundary condition that reduces or help us to reduce the the matrix size or equation size. Then based on that you are supposed to solve the simultaneous equations in terms of U1, U2 and U3, or maybe n number of parameters. Once you have figured out the U1, U2, U3 and up to UN, you can use those information and put into the prescribed formula for solving sigma element, say strain on element or reaction forces at element. In the part 2, we will be going to cover the numerical for especially bar and truss problem. Thank you very much.